And now we should be recording. It's weird how it says for each of you, like Taylor Bendel has temporarily joined the chat. Caitlin Norton has temporarily joined the chat.
It's weird for mine because I feel like you're just talking to your computer. But...
Oh, right. Okay. Yeah, it's funny that it says like how would it even know? Also, who would permanently join a chat? Or maybe it's something where, oh, you know what? I guess like once the meeting ends, and that's the terrible thing about this. Like then y'all can't see anything. Like if I type something in the chat after class, you won't see it. So, which is kind of unfortunate. So. Okay. So unfortunately, we didn't talk about anything today. I need to recap a good amount of what I did last time. So, oh well. Okay. So here we have our general first order ODE. And what we want is an implicit solution with a function big F of t and y is equal y of t is equal to 0. Okay, so so to find that, we solve the scaled ODE. So minus mu f plus mu y prime is equal to 0. And so in order, so I won't go through this in the next thing again, but what we found last time are conditions that the function mu must satisfy to make the ODE easier to solve. So we want mu t is equal to minus mu y times f minus mu times fy. All right. Okay. So if we define a mu that satisfies these conditions, then I showed last time like how you could come up with a function capital F by integration. Okay. Now, okay, so I'll just remind that. Okay, and the function mu, in certain contexts anyway, is actually called an integrating factor for that reason, because it enables the ODE to be solved by integration if you can find it. Now, in general, for general ODE of this kind, a function mu, integrating factor, would be extremely difficult to find. But we're just going to focus on a couple cases, special cases of ODE where we can get a hold of mu. Okay, so let's see. So the three types I consider, I might not necessarily do all of them, but okay. All right, so so one kind of a first order equation that's always covered in introductory ODE courses is an exact equation. So I can make an assumption about mu. Suppose I let mu y be equal to 0. So in other words, mu is only allowed to be a function of t. So then the equation I have for mu before is going to be simplified because that term's going to go away. So now I have mu prime of t is equal to minus mu of t f of df dy dy. Okay. Now, so if I rearrange this, I have okay, actually, I don't want that. Now, the only way that this could work, the only way that this could be satisfied is it doesn't depend on only t. Now, that might happen possibly after simplifying this as much as you can, but if you find that that depends only on t, then at least you have an equation that depends only on t. Therefore, you have an ODE, hopefully a simpler one, but you can solve for mu. But because it has to be equal everywhere, we cannot have any y dependence. Similarly, suppose mu t is equal to 0. Similar idea. Then the left side of that equation is going to disappear, and I have mu prime of y f of ty must be equal to mu of y fy of ty. So what needs to happen here, since mu is only allowed to depend on y, after you simplify as much as you can't have any t dependence. So if that's the case, if any dependence on t on this equation cancels out, then you're good to go and you can solve for mu in that situation. And so in those cases, you're able to find the integrating factor. Now that's pretty limited. It's kind of funny is homework problems on exact equations have to be like terribly contrived just to be able to solve them. So it's like, doesn't sound very real world applicable, but that's what we have. Okay. Now, so I want to mention this just because introductory ODE courses always cover this. This is from a somewhat different point of view, but there's really other kinds of equations that are going to be more relevant to us throughout the semester. And this next one is actually a special case of exact. And it's called separable. Okay. So the ODE is said to be separable if f of ty can be written as a product of a function of t and a function of y. Okay. All right. So what happens to this equation in this case if I just substitute this form of f in? So I need mu t of ty is equal to minus mu y of ty times f, which is g times h, and then minus mu times derivative of this with respect to y. But that's going to be g again times h prime of y. Okay. So what we want to find out is so what would be a good way to, is there a way we could find a relatively simple function mu that would have this equation be satisfied? Okay. Oh, actually, I should put the variable dependence in here. So this here we have g of t, h of y, minus mu ty, g of t, h prime of y. Okay. All right. Now, I've done that sort of thing quite some time ago, and I know there actually is a relatively simple solution. Basically, by making simplifying assumptions about mu. Okay. All right. And actually, I do have some notes somewhere where I can look this up. But so simplifying assumptions would be like, what if you decide that mu is going to depend either only on t? So in that case, mu y would be 0, and this term would go away. Or mu depends only on y, so that term goes away. So then we just have mu prime minus mu prime of y over there. So things like that would
It depends on why. What about the?
What?
You said if it depends on why that.
If you decide that mu is going to be only a function of y, then mu t must be 0.
Right.
So that would go away. And then this would be minus mu prime of y. We could write it that way.
Yeah, okay.
Okay. Okay. Okay. So, in fact, what we'll do is, let's go down that route. Because to me, it's no fun if I just go to my old notes and look up the answer. Because also, we try to figure this out together. So,
all right.
Okay, I'll throw that breadcrumb out there. Okay, first I need to take a picture of a note so far. Yeah, that's unfortunate. All right. Let's see, I'll keep this there. I'll just get rid of this. And because finding a mu that satisfies this, just as is, that can be very daunting. But sometimes you can make a simplifying assumption and then all of a sudden the problem becomes tractable. Okay. Now, so I'm going to assume mu is a function of only y. So mu t has to be 0. So now what we have is 0. Well, I can move one term to the other side. So I have mu prime of y, g of t, h of y is equal to minus u of y, g of t, h prime of y. Okay. Now, what's really convenient about the equation now? That we didn't have before. How can we simplify this in a way that we could not earlier?
How can we simplify this in a way we couldn't have before?
Yeah.
And again, we're trying to solve for mu of
Yeah, so G and H are given.
G and H are given, and we're just solving for mu of y itself.
Right, and it would have to be in terms of P and or H. But right now, just algebraically, what can we do to this equation to simplify?
Divide the G and H off?
Careful. Watch out for derivatives.
Oh yeah, the G, just the G.
Yeah, G goes away.
Yeah.
Couldn't do that earlier because we didn't have a G here to cancel.
Right.
So already this assumption about mu being a function of only y has kind of paid off. And it made the equation smaller to begin with, but there's one term went away. But now it's simpler still because you get rid of that. All right, so now let's see what we have. Now I have mu prime of y, and I can divide both sides by mu. And assuming that this is divided by 0. So that's equal to minus h prime of y over h. Okay. So just by rearranging. So so what would be a perfectly reasonable choice?
U of y is equal to h of y? Or, no.
Almost.
U of y. Oh, yeah, cosmos, but h prime of y? Alright. Negative h of y?
Oh, you know what? I just realized something. It's not as simple as I thought. Because set mu equal to minus h. Then you make this fraction, and they cancel out. So
mu equal to minus h.
So if I have minus h prime over minus h, but that's h prime over h, whereas I really need to be h prime over h. So that's so close. All right. So instead, so that didn't work. Let's look at this again. I'm going to rewrite this equation a different way. Mu prime h plus mu h prime is equal to 0. Does anyone recognize where that expression comes from?
That is a chain rule? I know, sorry, product rule.
That is a product rule for differentiation. Perfect. So that means that derivative of mu times h is equal to 0. So what can we infer from that? Okay. Okay. So Taylor or Caitlin? If the derivative of mu times h is 0, what does it tell us about just plain old mu times h?
Yeah.
Okay. I'll give one of them a little time to chime in, and if not, then you get it.
It's a
The audio cut off, but I believe you said it's a constant? So,
yeah.
okay, great. Yes, mu times h is equal to some constant c. So mu is not equal to like h or minus h, but rather c over h. Now, mu is a scaling factor of a whole PODE. So let's just try mu equal to 1 over h. Just for convenience, because yeah, it's an arbitrary constant. Let's just choose a convenient constant. Okay. So let's see what that does. When we go back to the original ODE, and we have to multiply both sides of the ODE by mu. So okay, so we have y prime is equal to f of t y. So if you don't know what f is, y prime is equal to g of t h of y. But then mu y prime is equal to mu g h. But mu is equal to 1 over h. So the h's cancel. So now I have y prime over h of y is equal to g of t. Now, does anyone remember, this is what I call separable equation. Left side depends only on y. Right side depends only on t. Does anyone remember how you proceed from here? When you have a separable equation and now it's separated, what do you do to solve it?
Don't you integrate both sides?
Yes, you integrate with respect to what?
I guess. Why? Is that wrong? The T.
It's half right.
I don't know.
Okay, you integrate both sides. What do you integrate with respect to on each side?
I probably should know separation variables.
Anyone?
I have to see like a visual number example from
Well, I guess if I look at it this way, it's the same as saying since y prime is dy dt.
Okay.
So then it's like you rearrange the equation, you think of dy dt as a fraction.
Oh, okay, because you want to get You do it with, like, with respect
Yeah.
to the proper one.
So more specifically, I integrate the left side with respect
With respect to
to
y and the right with
right side with
yeah.
respect to t. Now, that's always what they tell you. I never liked that. They just say, oh, you just do that. Now, I'm going to show you the more rigorous way why that actually works. So really, the more rigorous answer is you integrate both sides with respect to t. So I have 1 over h of y dy dt is equal to g of t. And now, if I integrate both sides with respect to t, okay,
That's a g prime of t on the left, correct?
just g, not a prime.
Oh, sorry, I was thinking about that. Okay.
Oh, that's a smudge.
Yeah, I was confused. Okay, that makes more sense.
Okay. But then, what can you do with the integral on the left?
The dt's cancel.
You can think of it that way, or more properly, use substitution.
Okay.
So if I let u equal to y of t, then du is equal to dy over dt. But then we don't really write u, because that's kind of non-intuitive. We just use y. So that's what leads to integral of 1 over h of y dy is equal to integral of g of t dt. And better yet, these are indefinite integrals. If you use a definite integral, like from 0 to t here, and like what the initial y value to y of t is the upper limit, then it makes it easier to take initial conditions into account. But we're not going to worry about that now. But yeah, so that's why that works. It's actually a u substitution that, because if you're going to integrate both sides of an equation, really what you're supposed to do is integrate both sides with respect to the same variable. But then you do this substitution only on one side. And that's why it looks like you're integrating the two sides with respect to different variables.
Sorry, I'm still just wrapping my arm around the last few steps.
Okay.
U is equal to y of t. That means du is dy over dt.
Yeah, so that whole thing becomes du. So what, if you were doing this like in a Cal 2 class, you'd have integral of 1 over h of u du. But then that's sort of non-intuitive to use the letter u.
Right.
And really you could use whatever letter you want.
Right.
Some people use y.
Okay.
Even though we were just using y earlier.
Okay, I gotcha.
Because u is y.
So you're explaining it, that's why separation of variables works, but nobody ever says that's why it works. Okay.
Yeah, because the way books present, it's like, oh, okay, but everything depending on y on one side of the equation, everything depending on t on the other side, integrate with respect to y here, integrate with respect to t here. Voila, it works. And it's like, shut up.
Not really, just not. So it'd be saying on the other side, you kind of do a u sub, and see it works out.
Yeah, and some books might explain that, but this ones I've seen or used years ago didn't really bother doing that.
I don't know why it never bothered me to think about why separation of variables work.
Yeah, well, at that point, it's like, okay, here's a problem, just tell me how to solve it.
Yeah.
Right, so any questions, including from Peanut Gallery, of what happened here? And I'm sorry if I end up, wait, I want to make sure I actually capture everything that's on the board. Well, and I'll get the picture while I'm at it. All right, so that's the second kind of equation that I want to look at. Okay. Now, now the third kind that is of most interest, most relevant to what we'll be doing later. Okay. Okay. So the third kind is a linear equation. So in this case, we assume that f of ty is equal to some coefficient p of t times y plus some other function q of t. All right. So if I go back to the equation that defines the integrating factor mu, if mu t is equal to minus mu y f minus mu fy. Okay. Now, so if I fill in this form of f in here, so mu t is equal to minus mu y py plus q minus mu df dy. Well, derivative of all this with respect to y, this is a linear function of y, is just going to be p of t. Okay. All right. Now, at this point, this is still not easy to solve for mu. But what we can try is, once again, see if we make a simplifying assumption about mu, so that this can be solved. Like before, if you assume that mu is a function of one variable, either t or y, then that will certainly simplify this equation. So, anyone suggest what we could do? Like, we want to make mu simpler, have it depend on only t or only y. So then the opposite derivative would be 0. What might be a good candidate for that? Yeah, so for example, if you assume that mu depends as a function of only y, then mu t is 0, or vice versa. And the goal is to make the equation simpler.
Okay, wait, say that one more time. If mu only depends
On y, then mu t is 0.
Then mu t is 0, so maybe the other way then.
Okay, so if we assume that mu is a function of only t.
Right.
Then
everything.
Okay. Oh, we don't have much time left, but that's okay.
But we just have a straight up mu over here.
Yeah.
I read about that one.
Yeah, so I'm going to let mu equal mu of t. So mu y is 0. So now we have mu prime of t is equal to minus mu of t p of t, which is great because then mu depends, the whole equation depends only on t. Y has been taken out of the picture entirely. Okay, so now we have this equation. So now I have ODE to solve for mu, which is funny because we're trying to solve for y. We're solving an ODE. So we got to solve an ODE to solve an ODE. But I write it this way, mu d mu dt is equal to minus mu p of t. What property does this ODE have? What kind of ODE is it? It is separable, so it's a good thing we already talked about separable. So we have, so using the way it's normally covered in textbooks, minus 1 over mu, actually 1 over mu d mu is equal to minus p of t dt. Okay. So then I can go ahead and integrate both sides. So now we have natural log of mu is equal to this integral. So then mu of t is equal to what?
E to
The exponential of this, e to the minus integral of p of t dt. So that is our magical integrating factor that makes it possible to solve the ODE. Okay. Now, all right, let me just check this here. Okay, now, last time I outlined a procedure like suppose you found a magical function mu you need so that you could come up with an implicit solution. How do you apply that? So we could go ahead and do that. And actually, I do want to do that. But not in 2 minutes. So, yeah, so that is where I will pick up with on Tuesday. Okay, so don't have any homework for you guys yet, but we'll get to that at some point. Okay, let me get one more picture. So you can see all of you in half an hour. All right. Oh, I gotta stop this recording. Okay. So catch you all soon enough.